Okay, moving on with the review sheet. So we have a car traveling at 50 miles per hour when the brakes are fully applied, producing a constant deceleration of 22 feet per second squared. What is the distance traveled before the car comes to a stop? So I'm not exactly sure what approach my student's professor recommended. However, I do know that this is a classic physics problem. There's no question about that. It's a classic physics problem that typically features these formulas here. So personally, I'm comfortable using these formulas. However, I'm already seeing an issue where this is in miles per hour and this is in feet per second. So we're going to have to do some unit conversion. I'm going to say let's commit to feet per second just in general. So we want those units to be the same. So we're going to say that we know that 50 miles corresponds with 1 single hour. So one way of doing unit conversion is to set up this sort of chart. Now it is the case that 1 hour is 60 minutes, and I purposefully put the word hour up here so that this word would cancel with the word hour over there. Also, we don't want the word minute in there in the final analysis, so we'll say that 1 minute corresponds with 60 seconds. Now, we do want the word seconds in there in the final sort of, the units that we're going to be using. So that belongs there. We don't want the word miles. We want the word feet in there. So we're going to put the word miles down below. So we're going to say 1 mile corresponds with 5280 feet. Okay, so that's a word that we want. We want feet per second. So what we've done is we set up a structure that would result in the word feet being over the word second, and all the other words that we don't want cancel. Miles cancels with mile, hours cancels with hour, minute cancels with minute. The only words left are the ones that we want, and then we can multiply straight across with the numbers. So after multiplying 50 times 5280, and then dividing by 60 times 60, it is 73.3 feet per second. So that's actually the initial velocity. Now that's helpful because at the end of the day, we want the distance traveled before the car comes to a stop. So ultimately, that's going to be a matter of using this one or this one because delta x means the horizontal distance covered or traveled. Okay. Now, this one looks kind of nice actually because it's relatively simple. Um, and which one you choose really depends on situation. But this is v sub I, which means initial velocity. V sub f means the final velocity. And I think we would agree that the initial velocity, well, we just found that it's 73.3 feet per second. 73.3 feet per second. The final velocity is zero because we're coming to a stop, right? So the final velocity, the target velocity at the end of the analysis is zero. Now, it is the case that we do not know what t is, so we will have to go on a separate mission to find out what t is. And once we find t, then we are basically done. We just plug it in here and then we'd be done. So there has to be a way of finding t. Well, it turns out there is. Right here, we could say that the final velocity is zero, so I'm going to write zero there. The initial velocity is 73.3. Now, A stands for acceleration. Well, we have a deceleration of 22. So since it's deceleration, it's going to be negative. So that's going to be negative 22 times t. So clearly we could add 22t to both sides. And then we would have this. And then we could divide both sides by 22. And that would give us 3.3, so approximately 3.3 seconds. Okay, now these are approximations. I am rounding everything. So it would be approximately 3.3 seconds. So in other words, once you hit the brakes, it takes you 3.3 seconds to actually come to a stop. Well, like I said before, once we have that number, we can then plug it in here. So at the end of the day, we are looking at, let's see, it would be 1/2 times 73.3 times 3.3, and that would turn into approximately 121. Now, once again, um, for my student at home, just remember this is a common approach, what we just did, to rely on these equations and also pay attention to what the professor insists upon when it comes to these. Okay, so problem number 20. A projectile is fired vertically upward from ground level with velocity of 1,600 feet per second. If air resistance is neglected, find its distance s of t above the ground at time t. What is the maximum height? Well, in this case, we're dealing with really the same equations, only now we're taking gravity into account, okay? So G is gravity, and since gravity is a downward force, it's going to be a deceleration. So that's why the negative is sort of built in already there. Now, gravity is typically seen as 32 feet per second. We are looking at feet per second over here. So that's something to take into account. The G in this case is going to be 32. All right, G is 32. We can say feet per second squared, actually. And this tells you the height. So before we had delta x in the last problem, that's horizontal displacement, whereas this gives us vertical displacement. So the height at any given moment in time, if you have a projectile being shot upward, would be dependent on, the velocity and how much time has gone by. Okay, and this negative once again represents that decelerating force of gravity. So I'm going to say that this is going to be a very similar approach to what we did last time. In fact, I'm thinking we could use really the same formulas too. I think last time we used a formula that looked something like this and a formula that looked something like this, and I think we can go ahead and do that. Now, I'm going to put little asterisks next to the formulas we're going to use. First of all, let's find out how much time this projectile spent in the air. We're gonna start with this one just to find t, because if the last problem was any indicator, we're certainly going to need t. So let's actually find that out by using this. Now the final velocity is 0. There's this moment where, after you shoot something in the air, there's a moment where it stops moving and then it starts moving down, right? And it's that moment where it stops moving, that's the peak height. You could think of it that way. That's the highest that it travels upward. That's the moment of peak height, I could say. And therefore, the final velocity is 0. It's that moment where it's just changing direction from up to down. And then we have the initial velocity, which is given here at 1,600 feet per second. So that's just going to be 1,600. And then we have minus 32 times t. So of course, adding 32t to both sides would give us that, and then dividing both sides by 32 would give us 50, and that would be 50 seconds in this case. So we found our t. So in other words, a projectile shoots upward and it travels for 50 seconds, and then after 50 seconds it stops, and that's when it starts to go down again. Okay, now we want to know how high it went, and that's where we're going to use this formula, because that tells you delta y, which means the change in height from the beginning all the way up to, you know, to the maximum, and then down again, maybe depending on how much time we're looking for. But we know that when the time is 50 seconds, that is when it's at its maximum height. So we're going to use this. So therefore, we have delta y equals 1/2 times the initial velocity, which was 1,600, plus the final velocity, which we know is 0. So I'm just going to leave that. And that's going to be multiplied times 50. So when you calculate all that, it becomes 40,000. So this went up 40,000 feet. Now, let's see. Find its distance S of t above the ground at time t. What is the maximum height? Yeah, I feel like this is really the same question. Find its distance S of t above the ground at time t. What's its maximum height? Well, I guess, to be fair, what they really mean here is what's the formula that you need to use. Well, you would use either this one or this one, actually. So just to be clear, this one could have worked as well, okay? So, so again, for my student at home, look over your notes, find out exactly how your teacher wants you to do this. But just know that, again, we could do it this way. This is the formula that you'd use to find T. G is going to be 32 feet per second squared, okay? Always pay attention to the units. This is feet per second. Had there been other mention of like miles or something, we would have had to convert that to feet. If there was mention in the problem of hours, we would have had to convert that to seconds. So you do need to make sure that all the units are the same. In this previous problem, they were trying to be tricky with you where it was miles per hour, but here we had feet per second. So you have to turn that into, if 50 miles per hour is how many feet per second, you have to figure that out. Okay. So yeah, that is the answer to that. The maximum height's 40,000 feet. The distance S of t above the ground at time t, well, you could have been like S of t equals 1/2. In this case, it would be 1600 t. That would have been a very valid function that you could have used, also known as 800 t if you simplify that. And you could have also modeled your function off of this one, where it would have been 1600 t minus, ultimately, since gravity is 32 feet per second squared, 1/2 of that would be 16 times t squared. Okay, so in my view, these would have been valid functions that you could have used to find the distance S of t above the ground at time t. Okay, so now we have find the antiderivative of all this stuff. So let's take a look at this situation. Well, first of all, it is really 1/2 times x to the 1/2, right? Isn't it? And then we're going to be adding 2 times x to the negative 1/2. So at the end of the day, they're just asking us to find the integral of that. And I'd say that's pretty straightforward. That's going to be 1/2 times x to the 3/2 all over 3 over 2 plus 2 times x to the 1/2 over 1/2, and then it's plus c. So at that point, you could always keep in mind that anytime you divide by a fraction, it's really the same thing as multiplying by the reciprocal. So really what we're dealing with is 2 over 3 times 1/2, which is going to be 1/3 x to the 3/2 plus 4 x to the 1/2 plus c. And really, that's kind of the answer. You could always represent this as the following, though, as well. Okay, so those fractional exponents you could convert to the radical version. So that is the answer to that one. Okay, so now we want the integral of 3x raised to the radical 3 dx. I would prefer to put the 3 on the outside for now, so that's that. And yeah, I mean, it's really actually straightforward at that point. In order to find the derivative, well, the 3 is kind of hanging out on the outside, and it would be x raised to the radical 3 plus 1 all over radical 3 plus 1. And don't forget the plus c. So, yeah, it's an odd looking problem for sure, but it's pretty much the answer. Pretty much the answer. So I'm going to write it like this, though. Let's put this kind of fraction type thing on the outside, and we'll put the x next to it, and then we'll have this as clearly the exponent. In fact, I'll wrap it in parentheses, and then we'll have plus c. So very awkward answer, and nonetheless true. There wasn't anything fancy necessary here. For example, we didn't need u substitution because even though we're not used to having a radical 3 as the exponent, it's still just a number. So you could just apply the power rule of integrals where you add 1 to it and then just make sure that the sum, that result goes in the denominator as well. All right, so that's that one. This one probably would be u substitute. Actually, no, I don't think it requires u substitution either because I see no reason why I can't just distribute that y to the negative 3. I mean, I know it's weird and no one wants to deal with a y to the negative 3, but I mean, the bottom line is you could distribute that, and when you do that, I think it would become y to the negative 2 plus y to the negative 3 dy. So there we go. And then just straightforward power rule would lead to y to the negative 1 over negative 1 plus y to the negative 2 over negative 2 plus c. I see no reason why that can't be the case. And then we have negative 1 over y minus 2 over y squared plus c. So that would be a way of converting the blue to the green. So that should be that one. Okay, well, cosecant theta over all this stuff. So let's take a look at some of the integrals as they relate to trig functions. So here's a list of the derivatives of various trig functions and the antiderivatives of various trig functions. I do not see necessarily how any of that's going to help us right away. So sometimes what I like to do is just get clear about what cosecant is in like a converted, as far as the fact that it's a reciprocal identity with sign. So let's just write that up top instead, because we know it's a reciprocal identity. We know that this is another way of writing the original antiderivative. Now, if we were to sort of consolidate this, that would be a matter of multiplying the top and bottom by sign. And therefore, I'm going to start color coding the yellow box and the red box. So with regards to the yellow box up top, that just remains that for now. But down below in the red box, that would turn into 1 minus sine squared over 1 minus sine squared theta over sine theta. Now what we have is a fraction divided by another fraction. Whenever you have a fraction divided by another fraction, you could really just multiply the top fraction by the reciprocal of the bottom fraction. So I'm going to suggest doing that. So really what we have is 1 over sine theta. This should be a d theta here. 1 over sine theta times sine theta over 1 minus sine squared theta. That's d theta. And as a result of that, we have some other business we could take care of, including canceling these. And therefore, we would end up with 1 over 1 minus sine squared theta d theta. Now, that is due to the Pythagorean identity. That's cosine squared theta. So we could certainly note that. So it's really 1 over cosine squared theta d theta. It's also the case that that is, we could say that that is secant squared theta. In case that's not clear, it's because 1 over cosine theta is secant theta. There's that reciprocal identity. So 1 over cosine squared theta is going to be secant squared theta. Okay. Now, it's the case that there is mention of secant squared theta right here. So we know that the integral of that is just tan. So it turns out, did you need to sort of know these a little bit? Yes. And it turns out you also needed to be aware of the reciprocal identities. Okay, so I'm going to bring this over here. We're going to make this a little bigger. You needed to also be aware of the fact that cosecant is really 1 over sine theta, which would apply here and here. You would have had to have the insight to consolidate this by getting a common denominator. We did that with the red box. We also recognize that there's a fraction over another fraction, which means you could multiply the top fraction by the reciprocal of the bottom. That resulted in these cancellations. You also had to be aware of the Pythagorean identity as it pertains to 1 minus sine squared theta. That's definitely cosine squared theta. And then you had to be aware of the fact that, oh, we have 1 over cosine. What does that remind me of? Oh, yeah, that's right, secant. But it's not 1 over cosine. It's 1 over cosine squared. So therefore, it's secant squared. And then you would have had to realize that this is the identity, or, well, this is the integral, the antiderivative that we need to work with. Okay, so that is how you do problem 24.